to be, which is passed to one of those smart contracts, is effectively recorded. You can query the blockchain without recording information. You can't store stuff on a blockchain or alter information on the blockchain. And so there's a ton of different blockchain networks, and they all work slightly different about how they develop distributed applications, or blockchain applications, or smart contracts, or chain code, as you might hear it called. And they all have different names for it. But fundamentally, there's tons of them. You'll hear Ripple, Bitcoin on the public networks, and the permission networks, which basically are ones where we invite members, not public networks, but not everyone can join, but they're private networks. Those are permission networks that usually use a certificate authority to understand whether or not the person's valid or not. And there's a few. One of the ones I work on and worked on for a while is Hyperledger Fabric. It's owned by the Linux Foundation. It's completely open source. I think it was originally developed by IBM, and then it was open sourced and put into the ownership of the Linux Foundation, where they've developed it ever since. Hyperledger is like the actual Hyperledger group has like 8 or 9 projects, different types of blockchain working on it. Hyperledger Fabric is one of those products. And Hyperledger Fabric is often the blockchain network which is being used to build business applications. I'd say there's 2 main ones. Ethereum is being used to build blockchain applications, and then other people are using Hyperledger. There are other ones, obviously, in the different industries and specific requirements and stuff, but most people will be using one of those 2. Hyperledger Fabric is what I'm going to talk about next, to give you an idea of how you build an application on Hyperledger Fabric, just to give you an understanding as to roughly how it works. It's different for Ethereum, but this is how Hyperledger Fabric works. So Hyperledger Fabric is a permissions network. So basically everyone in the network has to join the network, be added to the network by the other members. They're voted into the network. They can also be voted out of the network if they're malicious. When they're voted in, the infrastructure, depending on the network, but the infrastructure roughly looks something like this. You have member A, member B, member C, and they're going to have their certificate for joining the network, and they're going to have a number of nodes which do the transactions and the processing. Each one of these members can have a node they can have one or many nodes on the network, and each node is going to store a version of the ledger, and it's going to do the transactions, and it's going to run the smart contracts, or chain code as they call it in Hyperledger Fabric. The difference between Hyperledger Fabric and some other blockchains is they have a centralized ordering service. So it's slightly different to what I explained earlier about how they order transactions. In the open source version, they use Kafka. In AWS, it's chain code can be written in Hyperledger Fabric in either Go, and earlier I saw how many people wrote that. So you can probably follow along. You can write chain code in Node, or you can now write it in Java as well. It actually runs on the side of the chain. On every node in the network, it's running as a container. And these containers are on every peer, and every time someone calls stores the ledger, and it's executing chain code as transactions call for it, and it's endorsing transactions and storing them. Each of the monetary value, they could be number of assets, or they could be information or identification, or it could be anything really which you can codify. Let's have a look at an example of this. So this is an example from one of the 101 tutorials on Hyperledger. It's a tuna supply chain. And they use it because the idea is it's a supply chain from the sea, from fishing fish or fishing tuna, to actually the plate in the restaurant. And they chose this because there's a big problem in the tuna supply chain where there's a lot of fraud. People lie about the origins of tuna, where it came from. They're only fished in certain places and stored in certain places. So it's trying to codify that supply chain. This is an example which is not a cryptocurrency. This is trying to codify a supply chain of tuna shipments. And the whole purpose of this, we're trying to give this supply chain transparency. We want all different members in this supply chain to be able to see what's happening in the network. So in a tuna I can't even say tuna supply chain, we've got Sarah, a regulator, Carl, and Miriam. Sarah's a fisherman who sustainably and legally catches tuna. There's a regulator which verifies it. Carl is another restaurant owner which wants to also buy tuna from Sarah. But Sarah might want to sell at different prices to different people. On a regular blockchain, this wouldn't be possible because everything's public. But there's a concept in Hyperledger where you're basically running multiple blockchains, multiple ledgers, and we call those things channels. And we could set up a channel, 3 different channels in this network. One channel which stores all the information about the tuna, and then one channel which stores deal information between Sarah and Miriam, and one which stores deal information between Sarah and Carl. So it allows Sarah to privately sell information or sell tuna to Carl without Miriam being able to see how much Carl is paying for that tuna. It's a constant requirement in most businesses that you don't want the deals to be public, all deals to be public. And Hyperledger allows you with channels to have as many channels as you want, well, in a network, so you can create all kinds of scenarios which there's different levels of privacy on a blockchain. This is the overall architecture of this network. Sarah, the regulator, Carl, and Miriam don't write code. They work with applications. These applications are websites. They are mobile phone applications. These mobile phone applications are calling into blockchain services which store the information on ledgers. It's just like calling into a database, really. There's an API which you call tuner, so when tuner is caught, query all the tuner in the system to query a specific piece of tuner or update the holder of the tuner, who owns that tuner at that particular time. And in this network there is 4 peers, 4 instances, 4 virtual machines in the network, and those peers, some of them can see different chains. There's 3 chains, one which is recording the tuner shipment, this is called a channel, one which is storing information between Sarah and Carl, and one which is storing information between Sarah and Miriam. And the important thing to know is that the regulator can see everything which is happening. Sarah can see everything which is happening, but peer 2 can only see Sarah and Carl's information and this recording tuner shipments, and peer transactions among specific members of a network. You can create update channels, you can build new ones by creating a configuration file and submitting it to the network, and that channel will be created on all of the different peers which have all been allowed to. And basically you can induct peers, so if you want peer 3 to be added to that channel, you can add them to the channel and they'll start recording that. It's not important, you know, we go, but we'll just start with creating basically a class file. And we're going to have a structure which stores our tuner. And that structure is going to store things like the vessel which the tuner was caught on, the date and time where it was caught, the location where it was caught, and the holder, the person which owns that tuner at the moment. When you instantiate a piece of chain code, you call a function called init, initialize. And for the purposes of this demonstration, we're initializing some fake tuner into our network. And we add the network tuner as just like objects, and we're ultimately adding the tuner here in a for loop for all of the array of tuner. We're storing it into put state, we're storing it into the blockchain network. So now we're going to have a ledger which contains that tuner information. Sarah, in her application, when she catches new fish, she's going to call record tuner, which is a method on that chain code. And it's going to change the state and add new fish to the network, to the ledger. Miriam is going to be able to call query tuner to find out where a specific piece of tuner has come from. And it's going to read that from the ledger. And she's also able to change the holder who owns that piece. She can change it to herself. She can say, I now own that piece of tuner. And the regulator, they can query a specific piece of tuner, but they also have the ability to query all tuner in the network. So they can see all of the current scenarios, all the current state of the network. This is an invoke function. You only get 2 functions in chain code. You get init and invoke. Well, I've just said I want a number of different functions there. So the way that we do that is in my invoke function, I take one of the arguments, and that's effectively going to call different functions in the chain code. So you'll see, if I pass in one of the arguments as query tuner, it's going to run a query called query tuner. If I pass in init ledger, it's going to initialize the ledger. If I record the tuner, query all tuner, change tuner holder, it's going to call different functions. So what I've done is basically added a method in there to allow me to call different functions in my smart contract. This is the query tuner function. It takes a number of arguments in a string. If the arguments is not has the correct number of arguments, it's going to pass through. If not, it's going to error. Incorrect number of arguments is expecting 1 argument. It's going to go and get that particular piece of tuner from the database, from the blockchain, and return it back to the user. A query method isn't going to create a transaction on the blockchain. It's just reading the data. If we record the tuner, which is what Sarah's going to do when she catches fish, she's going to record the tuner. She's also going to be passing over an argument string. There should be 5 arguments which are passed in. But then my click is not going to just carry on working. So there we go. And we can see, based upon the arguments are passed in, we create a new piece of tuner. We pass in the arguments, which create one of the arguments is going to be the vessel, the location, the timestamp, the holder. It's going to convert it to bytes, and this is just some code which basically stores that on the blockchain. That will also create a transaction on the blockchain. And then we're going to change the holder of that, we have a function which changes the holder of that piece of tuner. And what we do there is effectively get a piece of tuner out of the database, we modify that person's name, the holder name, and we put it back in the database. Again, it creates a transaction on the blockchain, but we see this update happened. That transaction is stored in a block, that block is added, and we have a kind of log of all the transactions which have happened on our blockchain. If we want to install a piece of chain code, there's a command line interface. You probably would use the command line interface, you probably use some kind of deployment, but this is roughly how you do it in command line. We go peer, channels, when the CLI is installed on one of the peers, install, give it a name, tuner chain code, give it a version number, version 0, and we're going to use a file, source chain code underscore tuner, and the go folder. It's going to create that into a Docker container, it's going to distribute that across the network to all of the peers. All of those peers are going to have that Docker container, they can execute that code. You could check or list all of the chain code that's installed on a particular code, so we'd say chain code list, it will list all of the pieces of chain code that are stored on our network. And this is roughly how we actually execute functions. We use an invoke method. And we'll see here that you've got invoke on my channel, invoke the piece of smart code, the chain code called tuner chain code. This is the arguments we're going to pass in, so this is the invoke method. And we're going to pass in a method called query tuner. I should actually pass in another argument there, which is the ID of the tuner. This is probably going to fail if I actually ran it. I didn't actually run it. So I should pass in like a tuner ID as well to query a specific piece of tuner. And then some other options, and I sign this particular transaction as well with my certificate. And we can take a command line. This is the application we built, a Node website. It executes the same thing as the CLI, but just done in Node. We can write this in any language effectively. And you see here we've got a very simple front end where I can query all the different tuner. I can query a specific tuner catch. I can create a record tuner, a tuner in the database, and blockchain code, which is at the top, but that's actually running on the peers, not locally. And I've got my application, it's got App.js, it's a Node application, an index.html. I've got a piece of code which runs all the different transactions, and when they press the buttons, it runs the pieces of code which ultimately affect or query the ledger, the blockchain. This is how we construct a transaction in Node. We put a request, we pass the chain code ID, the piece of chain code we're going to call, the function that we're going to call, the arguments for that function, the channel which we're going to run it on, and give it a transaction ID, and then we say channel.send transaction proposal. It sends the transaction to all the different things on the network, and then it's endorsed, verified, ordered, put into a block, stored on the blockchain. Now, blockchains are quite complicated. Not everyone, most people in fact, which we speak to about blockchains, have got a use case of blockchain. They actually don't need blockchain. All they need is a ledger, which is cryptographically secure. So, although they do definitely need blockchain, there are scenarios where they definitely could use a blockchain to solve the problem they're trying to solve. So, what we did at AWS was we created two different services. One, which is called the Quantum Ledger Database. It's a centralized database which works a bit like a blockchain ledger. We basically store a history log of everything, but it's a central database managed by one single person, so it doesn't have that distributed effect. And then on the other side, we have an Amazon managed blockchain service. Now, the Quantum Ledger, just to quickly explain what that is. Blockchains are quite cumbersome, quite difficult to set up. There's lots of moving parts. You might not want that, but you might want a cryptographically secure log which can't be adjusted. We have one at Amazon. We use it privately, and we basically opened this. We call it Quantum, the project, and we use it in our own systems inside Amazon. We enable public so that anyone can use it as a way of cryptographically storing ledger information. And it basically works in the same way as a blockchain works, but it's centralized. One person owns it. It works a bit like a database. So, to be fair, it's a DMV scenario where someone writes something to the journal. They run an insert, and insert a car into the system, they update the car, and then they delete the car. Now in a traditional database, it would just be affecting a single row, but in a quantum database, in the quantum ledger, what happens is we create a blockchain of all that information. We have a complete immutable log of all the information that took place. So it's a scenario which some people are being used. We have healthcare directors, a customer which are currently using our quantum ledger database. Healthcare operates a heavily regulated industry. It's critical that our compliance data is correct and auditable with history. That's why they're using quantum ledger. They don't require the complexities of blockchain, they're not in a consortium, they don't need to share data, but they do want to have a way of having an auditable trace in their ledger, so they're using that particular service. We also have the Amazon Managed Blockchain Service, and this basically manages two open source frameworks, and you can choose either Ethereum or Hyperledger Fabric, the fabric that I just showed you a moment ago. But creating a blockchain network on your own is a bit like creating Kubernetes on your own. It's hard, difficult, lots of networky stuff, lots of instances and stuff. It's basically a managed service where we will create a blockchain network for you. You can build your own smart code, chain code and install it, or smart contracts and install it on those networks. You can manage who's part of your blockchain, who's not part of your blockchain, and it will scale really well. It's less expensive than running all of the infrastructure yourself, and you just buy it as a service effectively. So it's an easy to create blockchain service. You can choose between Hyperledger Fabric or Ethereum. I'm not going to go into the differences between these two, you can read up for yourselves, but fundamentally there's differences, there's reasons why you might choose a private blockchain network, and there's reasons why you might choose a public one. And it really depends on what your use case is, as to what one you're going to be using, and maybe whether you need to use blockchain at all. We have customers already using this. It's in public preview at the moment. Guardian, giving our vast partner ecosystem, we're exploring the decentralization and immutable tracking benefits of blockchain for potential applications in insurance business. We believe blockchain can improve the transparency and efficiency for stakeholders in these networks to transact. So they're using blockchain because they want to, they've got lots of multiple people involved in an insurance claim, and they're trying to make that business process simpler and more transparent. Use case. You might use Amazon Quantum Ledger Database. You might use an Amazon Managed Blockchain with Hyperledger. You might use an Amazon Managed Blockchain with Ethereum. Or you might use a traditional database. I'd say probably 80% of the people which come speak to me about blockchain would probably be better off using a Quantum Ledger or a traditional database for their scenarios. But there are definitely use cases and specific distributed requirements that mean blockchain is the way that would help to, it would make is a better way to build an application. So hopefully I've just shown you in this talk a little bit about what these services are, what blockchain fundamentally is, and what developers can do with blockchain. Because I think if you go to a blockchain meetup or blockchain events, quite often people will talk about blockchain, and they'll talk about ICOs and cryptocurrencies. And really, as developers, that's not where the interest of blockchain is for me. These slides I'll make available afterwards. And hopefully I've explained a little bit more about blockchain for you. If you've got any questions, we're running a little bit late, so I'll be in the foyer having lunch with you all. So if you've got any questions, please do come up and speak to me. Thank you very much for listening.
Good morning. Or let me try this. Goedenavond. Nasılsınız? Cool, so I'm Kavya, and I'm here today to talk with you about locks. Now I take it everybody here is familiar with multi-threaded programming? Yeah? So you're you're all probably familiar with locks, and you probably just love locks. No, right? We all use locks, but locks have this big, bad, scary reputation. And this is for good reason, right? We probably all heard about or worked with systems where the use of locks caused performance problems. Here's an example from one of the services, production services where I work at Samsara. Now this is a critical component of our read pipeline, so we care a lot about the latency of the service. And you can see one fine day, the latency went up by nearly 10x, and this turned out to be because of a locking issue that we'll come back to. So we know from experience, locks, kind of bad. But that said, you know what? This production service is written in Go, and the Go runtime uses locks extensively under the hood, as does your favorite database server and... In what scenarios do they perform well, and when do they cause a problem, and what can we do about it? These are the questions we'll explore today.
じゃあ、八村塁選手もかなりアメリカの大学に行って成長を一気にした部分もあったんですか？
そうですよね。やはり日本の国内にいると2メートルぐらいの選手がどうしてもインサイド近くにいましたんですね。そこでやっぱり行動することが多い。それがやっぱりアメリカの NCAA の大学に行った瞬間の1年、2年、3年で、アウトサイド、今のパワーファードと言われる4番ポジションでありますけど。
Okay, don't worry, I have you covered. All you need to know about Go today for this talk is that in Go, the unit of concurrency is called the Go routine. And Go routines are conceptually very similar to regular threads in a programming language like Java or C++. So you'd use them exactly like you use threads. But the big difference is that they are user space threads. What this means is the language runtime, Go, block. So there's no try acquire semantics. If a Go routine tries to lock and it doesn't get the lock, it will block. Okay, with that out of the way, let's talk lock internals. Or, better yet, let's just build a lock. Okay, so where do we start? Well, let's start with what we know and work backwards from there. We know we want locks to give us mutual exclusion, right? That is, say I have a very simple program. This is a task queue that's shared between two threads. On the right-hand side, we have the reader thread that's going to read from the task queue and process a task. And on the left-hand side, we have the writer thread, which is going to create work and put it into the task queue. So we know that here's how this will work. We have a flag. The flag is going to tell us, it's going to track whether the task queue can be accessed. If it's free, it's 0. And if the task queue can't be accessed, then flag will be 1 to mean it's not available, it's occupied. Okay, now... whatever, it reads it, and then it sets flag back to 0, and then it returns. If, however, it reads flag, and flag is 0, sorry, if flag is 1, it's in use by the other thread. So, what do? We just try again. It's just going to loop. Now, the writer thread looks exactly the same. On the writer side, we check to see if we do the same thing, say, for a couple of reasons, both of which come down to what finally gets run on the hardware. So first let's look at this line, this flag++. Now, the compiler compiles this down to this, in x86, to this increment instruction, inc. And the processor takes this instruction and runs it as a read modify instruction. So, read modify write instruction. So in 3 steps. It reads the variable from memory into a local CPU register, it modifies it, in this case it increments it, and then it writes it back. So this means that this one instruction results in 2 memory accesses. Why is this a problem? Well, what this means is it's totally possible when we have 2 threads for that read and write to be interleaved with the other thread's read. So in this case, it's totally possible for T2's read to start after T1's read modify write has started and still see the old value of flag, which is 0. Now this is called a non-atomic operation. And a non-atomic operation simply means that another processor or another thread can see the effects of the operation half complete. Now an operation can be non-atomic because it uses multiple CPU instructions. So for example, if you do a load or a store on a large data structure, or if it uses a single CPU instruction, but that CPU instruction results in many memory accesses, like the flag ++ we just saw. The opposite of non-atomic instructions is atomic instructions, and atomic instructions are indivisible. So in x86, simple loads and stores of data that fits within a single cache line is atomic, and it's guaranteed to be atomic, and this comes down to the fact that x86 is cache coherent, right? It guarantees that if you have many CPU cores, they are all going to have a consistent view for a single cache line. Okay, so atomic is what we want. Atomic is